orthogonal trajectories. Now, the word orthogonal means perpendicular. And, perpendicular means at a right angle. Okay? So a lot of times you'll see people use this notation. They sort of put two perpendicular lines with a little right angle box in the corner to indicate perpendicular. So if you look at this picture on the right, um, I want you to imagine you had a whole family of curves that looked like this. Then if you have this red line right here, this red line describes a curve that's an orthogonal trajectory to the family of blue curves. So you can see that wherever the red curve intersects any one of the blue curves, it's always at a right angle. Okay, so this would be an example of an orthogonal trajectory. So the orthogonal trajectory of a family of curves is a curve that intersects each curve of the family orthogonally. So let's take a look at the other example on the right over here. The blue curves this time are circles. And we have a whole bunch of orthogonal trajectories. Any one of these red lines here is an orthogonal trajectory that makes a right angle with each of those circles at a point of intersection. Okay, so what we want to do is we want to oftentimes find the orthogonal trajectory of a family of curves. So let's take a look at example 5 and let's see what we have here. We have a family of curves. This is x equal to k times y squared. And we want to find the orthogonal trajectory of this family of curves. So when you think about these curves, these are basically parabolas, but they're not parabolas that open upwards or downwards. These are like left-right parabolas. Okay, so normally your parabola is something like y is equal to x squared. This time it's reversed. It's x equal to y squared. And this k is basically going to give us different curves. So if I were to try to draw a picture to describe the situation, it's like here's our axis. We have a left-right curve. So, maybe one curve looks like this. And you could have another curve, maybe that looks like this. That's for positive values of k. If you had negative values of k, they would open to the left side. So maybe you have something that looks like this. You have something that looks like this. So this gives you a whole family of parabolas. So how we're going to find this orthogonal trajectory is the first thing we're going to do is we're going to find a differential equation satisfied by all members of the family. To find this family, we're going to differentiate both sides with respect to x. So when we do that, we're going to get 1 is equal to k times 2y times dy dx. Remember, we need to use the chain rule, and y is implicitly defined as a function of x, right? Y is a function. So what we see here is we see that we have this k here. So we need a differential equation that works for all k. Need a differential equation that works for all k. But we already have k being described by this function. So what I can do is I could use this x equal to k times y squared, and I can describe k as x over y squared. And then I'm going to substitute that into my equation that I got before. So now we're going to have 1 is equal to x over y squared times 2y dy dx. Okay, so we can simplify this a little bit. We can write this as 1 is equal to 2x in the numerator, and in the denominator we're just going to have a single y, and then we're going to have dy dx like this, which in turn gives us the equation y divided by 2x is equal to dy dx. So looking at this equation that we've arrived at, I hope you could see that this is a separable differential equation. We got the y's and the x's like that. I want to remind you that dy dx, these are slopes of tangent lines. Okay, so what we want is we want something orthogonal to that. So we want orthogonal to y over 2x. And remember that if we write our slope m2 and you want that to be orthogonal to the first line m1, it's negative 1 over m1. So then m2 will be the slope of the line that's orthogonal to m1. So in our case, what that's going to mean is that this guy is going to equal to negative 2x over y. So in the end, we end up with the following differential equation. We need to solve dy dx is equal to negative 2x over y. Solving this will give us our orthogonal trajectory. Great. So we have a separable differential equation. So this means that we can write this as y dy is equal to negative 2x dx. When we integrate both sides, let me put an integral here and an integral here. And then this is going to give us y squared plus c1 over 2, of course, is equal to negative x squared plus c2. Let's subtract c1 from both sides. So this is going to give us y squared over 2 is equal to negative x squared plus c2 minus c1. Let's move the x squared over to the left-hand side. We'll get x squared plus y squared over 2 is equal to, and then let's just combine that c2 minus c1 to one constant. Let's call it c. So this will be the answer. This is our orthogonal trajectory. When you look at this orthogonal trajectory, this is basically a family of ellipses. All right, everyone, take care.